This is a collaborative project between some researchers in UK, China, and also Australia. The configuration for the problem is fairly simple. So we have a cylinder, a vertical cylinder with a hemispheric bottom. It is oscillating and then generates some radiated waves. So we want to look at the viscous effects on such a free heave decay of the cylinder. We actually conduct both the linear boundary element method, basically it's a potential flow model, and also the CFD model in OpenFlow, and just to compare the results on the eddy mass and the damping coefficient. Okay, so this is a general overview of the linear frequency domain modeling. So we use actually a in-house code from Shanghai Jiao Tong University, where it's a typical frequency domain code. And you can see the mesh here. It's basically a boundary element method. And then what we try to do is that once we get the eddy mass and damping coefficient from the code, we approximate the cylinder motion as the exponential decay, the cosine function. And then we say that the damping rate is related to the eddy mass and damping coefficient. So by this way, we can approximate the decay motion, the velocity, and also the acceleration of this heaving cylinder. But it's just an approximation of the time domain solution. Yeah. Okay, so then at the same time, we actually did a CFD modeling in OpenFlow. Again, this is based on the classic two-phase flow model, where it's a Navier-Stokes solver with a VOF free surface tracking. We actually apply a high Reynolds number K omega SST turbulence model. Yeah, at that time we thought that it was quite a large scale body, and if you use a high Reynolds number, probably you can save a lot of mesh. But apparently this is discouraged by the reviewer. I think that one of the reviewer does not like this. Apparently, he hopes us to do a low Reynolds number without any wall function modeling. And then at the same time, we also apply the motion solver. So it's basically couple rigid body dynamics with the hydrodynamics. So in order to get the heave motion. This is just a overview of the mesh. We use a symmetric mesh, so x-symmetric mesh. So we approximate as a 2D case, and the total mesh is approximately, I think it's around 10K cells. Cannot remember exactly. Okay, so once we get the motion, the free surface, because what we can get from the CFD is the time series of the heave motion. So and also the force acting on the cylinder. So what we do is that we decompose the force from the time domain obtained from the CFD model, and then using express it as a first order Fourier series. And then we say that the eddy mass is aligned with the cosine function, the damping is aligned with the sine function, and then we can further extract the eddy mass and the damping coefficient from the CFD model. But this is again based on the linear first order Fourier series. And then if we have the eddy mass and damping from the CFD model, we can further compare with the eddy mass and damping from the linear potential model, where we can say that, okay, this is due to the viscous effects. The difference will be due to or attribute to the viscous effects. Okay, so first we just validate the CFD model. We did some experiments in the relatively good, very nice, towing tank in the Shanghai Jiao Tong University. And we have some, we have a cylinder that is restricted to heave only. using some mounting structures. So here, unavoidably, we introduce some mechanical damping due to these mounting structures. So we need to, we actually did some dry test to measure what is the extra damping introduced by the mechanical structures. And when we did the comparison with the CFD model, we have to take this into account. And this is the comparison between the CFD and the experiments. Generally, we say that CFD can nicely reproduce the real heave motion of the cylinder. Okay, so then we can start to look at the added mass and damping from both models. These two figures actually shows the ratio of the added mass and damping from these two models. So what we observe actually is that the added mass is nicely predicted by the BEF model. That's apparently due to the, it's dominated by the inertia effects. And the difference is generally within 4%. And with the development of the flow, actually, the deviation is further reduced. But if we look at the damping coefficient, it starts to increase from the second cycle. The first cycle actually is fairly close to the prediction from the BEF model. But if we look at the fourth cycle, actually the deviation reaches approximately 15% for such a case. But this deviation definitely, it depends on the geometry and also the other parameters. So what we do later, what we did later is that we try to see how this deviation is affected by the different parameters. So this is the effects of the initial displacement for the LMS and damping. So the ratio actually again increases with the increase of the initial displacement. But again, the LMS is quite nicely predicted, and the maximum is usually within 5%. But the damping coefficient actually reaches further to 25% if we further increase the initial displacement. And then we have the effects of the diameter. Again, it's well known that if you have a relatively small diameter, usually it's dominated by the viscous effects. But if you have a relatively large diameter cylinder, and then this wave structure interaction could be dominated by the inertia effects. And this is also, this also agrees with the results we obtain here. So the added mass actually, we can see that if we further increase the diameter of this cylinder, and it reduces from the 7% to probably 2% something, but the damping actually, it reduced significantly. So the viscous damping actually reduces from 50% to almost 10%. But even we say that the diameter reaches the 0.6 meters, this 10% is not a really small number comparing with the potential damping due to the free surface. And then we further look at the draft. So again, if we further increase the draft, the added mass and also the damping, the viscous damping coefficient actually increases, but not significantly like in the diameter effects. So here, for instance, for the viscous damping, it increases from 7% to about 25%. So this is just a simple parametric study to show that how these geometric parameters affects the viscous added mass and damping. So we further transform the viscous damping from the linear one, the B coefficient, to the quadratic ones. So what we do is that we assume this viscous force can be written as the half times the drag coefficient times the rho A and velocity squares. And this is the common way we use to empirically take drag into the account, where we need to identify a drag coefficient. This is expressed as KOZWaves here. But this identification of this drag coefficient in the potential model could be fairly empirical determined, So mostly we adopt some experiment data, for instance, from the steady state flow, and then we say that probably we can use this to approximate the drag coefficient. But is this really accurate or not? So we just try to transform the linear one into the viscous one and see what is the value of this quadratic viscous coefficient here. Okay, so we assume that the work that is done in the cycle by the linear viscous coefficient, linear viscous force is the same as the quadratic ones. So we can transform from B to KOZ by using equation 11. Okay, so then we try to plot the effects of the Reynolds number for this viscous coefficient. This Reynolds is sort of cycle-based Reynolds number. So this eta max here is the cycle, the velocity, the maximum velocity at each cycle. And then we also see what is the KC range. And we found that actually for most of the experimental data, the KC number actually is, falls within a fairly narrow range. So about from 0.5 to 1.5. So we just plot the effects of Reynolds number on the KC here. And we found that apparently the first cycle KC here is irrelevant to RE. That is because we say that the first cycle probably is still dominated by the potential ones. So you'll see that the KC here is fairly small. But from the second to fourth cycles, we observe that there is a trend, and we try to describe the trend as an exponential decay. And most of the data actually falls within the plus minus 30% of this exponential decay. Okay, so there might be some questions here. Let's say if we directly compare the linear potential model with the results from the CFD model, could be, what is the effects of the nonlinear effects? So we compare the results from Aqua with the linear potential model on the eta, the heave decay here. Surprisingly, actually, we didn't really find any effects on the nonlinear ones, so which means that the results from Aqua is more or less the same as the frequency results. So then we say that probably if you directly compare the linear potential model with the CFD model, the deviation is primarily due to the viscous effects. So in conclusion, what we have done is that we try to investigate the viscous effects on the added mass and the damping coefficients by comparing the CFD model with the linear potential model. And we found that the added mass effects are fairly small, within 5% for most of the cases, but we find a strong dependence of the damping coefficient. The first cycle damping is dominated by the inertia effects, but the viscous effects start to grow in the second cycle, from the second cycle. And then we see that the cylinder basically has a relatively small diameter and a large draft when your viscous is obvious. And then we try to transform to the quadratic drag force and see the relation of Reynolds number on the quadratic drag force coefficient. Okay, so that's all for my presentation. Thank you.
Yeah, thanks, Hao. That's very nice presentation. I guess there will be some questions or comments from the audience.